video, we're going to talk about partial fractions and partial fraction decomposition. Now, generally, partial fractions are going to be used in Calculus 2 when you're trying to do integration by parts. Now, in section 2.6, we saw that a polynomial with real coefficients could be factored into a product of factors with real coefficients, where each factor is either a linear factor or an irreducible quadratic factor. In this section, we show that a rational function can be expressed as a sum of rational functions, where each denominator is a power of a linear factor or a power of an irreducible quadratic factor. Now, for example, 3x minus 4 divided by x squared minus 2x is, you can rewrite that as 2 over x plus 1 over x minus 2. Each fraction in the sum is a partial fraction, and the sum is a partial fraction decomposition of the original function. Now, in this section also, you're going to need your calculators, and we're going to show you a couple different ways to do these partial fraction decompositions. Now, what we have here in this chart, this is simply just really what's going to be happening, how we're going to do this partial fraction decomposition. We're really not going to see example 1 or part 1 too much, but you do have to pay attention. If the degree of the numerator is bigger than the degree of the denominator, which you'll see in your homework, you will have to do polynomial log division first, then do the partial fraction decomposition. Now, the big thing here, we'll have to factor the denominator into a product of factors. Also, we'll have to put A's, B's, and C's over it. It's a lot easier if we just get into it. Now, we'll start with example 1. If you notice, it says, write the terms for the partial fraction decomposition of the rational function. Do not solve for the constants. So this is nice and easy. You just have to write the partial fraction decomposition. So the way we do this, this will actually equal A over x plus b over x squared plus c over x cubed, because we have x cubed here, plus d over x plus 3. Now the next part's a little bit different. Because x squared plus 1 is an irreducible quadratic factor, we're actually going to have ex plus f over x squared plus 1. That's the biggest part. Everything else is going to be a single letter, but if you have an irreducible quadratic factor, that's when you do the double letter like that, ex plus f. Or, and again, these letters don't have to be exactly this, but you always start with A, and you go until you don't have any more denominators. Now, if you look at B, you can actually rewrite x times x squared minus 4 to x plus 2 times x minus 2. So we can rewrite our partial fraction decomposition as A over x plus b over x plus 2 plus c over x minus 2. So that will be the start. Again, this can be written as the denominator in black there. So that's the first part of your partial fraction decomposition. First example wasn't too difficult. Let's move on to example 2. Now, denominators with linear factors. Examples 2 and 3 illustrate how the constants a sub I in part 3 of the partial fraction decomposition procedure can be found. Now, the book that we use actually uses a sub 1, 2, 3, 4. We don't have to do that. We can use A, B, C, and D. It means the same exact thing. Now, the big thing before we do this, we have to factor the denominator. That will factor to x minus 5 times x plus 3. So I can really write this as A over x minus 5 plus b over x plus 3. So what we can say is that 5x minus 1, because we're going to multiply both sides by x squared minus 2x minus 15, is equal to A times x plus 3 plus b times x minus 5. Now when we distribute the a and the b, we're going to get ax plus 3a plus bx minus 5b. Simplifying this a little bit further, we're going to put our a and b together, and we're going to put our 3a minus 5b together. This tells us then that because the 5 is in front of the x and a plus b is in front of the x, a plus b is equal to 5. And also, 3a minus 5b is equal to negative 1. Well, if we need to solve this like normal, I can multiply this equation here by negative 3. So I have negative 3a minus 3b equals a negative 15. Adding down, I'll have negative 8b is equal to negative 16. b is equal to 2. Now, if b is equal to 2, then a plus 2 is equal to 5, which means a is equal to 3. So once you have your value for a and your value for b, we can put it back into our original equation here. So we'll have 3 over x minus 5 plus 2 over x plus 3. So really, 5x minus 1 over x squared minus 2x minus 15 is equal to 3 over x minus 5 plus 2 over x plus 3. Now in your calculator, you'll be able to see this. We'll put them both in. So we'll have 5x minus 1 divided by x squared minus 2x minus 15. I'm going to make this bold here. So we'll have 3 divided by x minus 5 plus 2 divided by x plus 3. Now I want to make sure it is sequential so it can see it. So there's our two equations. Remember, parentheses are your friends here. So here's our first equation. And if you notice, our second equation follows exactly as it's supposed to here. So that just tells you that those two equations are the same. Now, if we look at b, we can really factor this times into x times x plus 2, which means I'm going to have a over x plus b over x plus 2. So that means 1 will equal a times x plus 2 plus bx. Simplifying this, we'll have here, combining my like terms, here's what we're going to have. Now here's the catchy part. There is no x value over here, so this will be 0x plus 1. So that means a plus b is equal to 0. And 2a is equal to 1. That means a will equal 1/2. Since a is equal to 1/2, that means 1/2 plus b is equal to 0, which means b is equal to negative 1/2. So if a is positive 1/2, b is negative 1/2. When you put that in, we'll have 1/2 over x plus a negative 1/2 over x plus 2. Now you could simplify this to 1 over 2x plus a negative 1 over 2 times x plus 2. That would be simplified, but really not needed. So when you check this in your calculator, we'll have 1 divided by x squared plus 2x. And then we'll have 1/2 x, or 1/2 divided by x, plus a negative 1/2 divided by x plus 2. I know it looks funny up there, but as we see this graph, you'll see. And there you have it. Okay? Exactly the same function.